GPUs and looking into how it works out. So it was a more of a learning experience for silicon manufacturers, and for us, the thing was like we wanted to really deep dive into massive compute, massive amount of data, and all challenges which it can pose. There's the other side of the thing. I mean, this is what possibly all of you would dream about. Can I have 1 petaflop of compute resident on my lab, just me using that? And can I have about, some 100 terabyte of a storage server where I can have all my data of whatever I need, and I have about 1 million images of whichever data set I'm looking at. That's what each of you would love. But then the moment you have that, there comes another big challenge, and that's about how you handle the data. So let me give you a briefing about what we were looking over here. So we looked at images from X-rays to CTs to MR to ultrasound. We looked into problems on compression, classification, image generation. We were working on, so I will come to the compression part later on, because that's essentially the key which we are trying to solve. We're looking into image classification for multiple diseases. So that had lungs, you had mammographies, you had ultrasounds of the brain, you had ultrasound of the chest, you have ultrasound of the cardiac vessels. Then we were also looking into image generation. A lot of these problems in terms of how do you generate more training data for pathologists, how can you generate more multimodal data, which is if you want to train models which can work well by taking in CT and MR or CT and ultrasound, you don't always have access to both CT and ultrasound. You will have to train, you'll have to learn to generate a different modality from one of those images of another modality. We had a lot of image generation going down over there, and then finally we were contributing into this set of tools and techniques which went over there. So in total, these were the different diseases we looked into, and the dissemination and the repositories which we created out of it. Primary contributors were these people, and there are another some 1.5 dozen contributors over there. I don't have the list right now. So there were students, interns, everybody working at different phases on different parts of it. So the prime challenge in a year of kickstarting this project was we had so much of data, we ran out of disk space. So the lab had a very nice 24 terabyte storage server, a NAS box, rate configured NAS 24 TB, which means you had 48 TB of disk space in the storage inside over there. And then we ran out of space in a year, and we were not even done with half of the work packages we were supposed to complete. So that's what was a need. We needed to really develop a data compression system in order to have everything stored. So we started working on very high density compression of biomedical images. So when I say very high density compression, these are 700 times compressed, which means that if in standard mammography would come to you with a file size of 35 MB, the compression factors of what I am telling you, this 35 MB of a mammogram would get compressed by 700 times, which means that it barely becomes about 170 KB in your file size. So that's the scale of what we are looking at. Now, we initially started with X-rays and mammograms. Eventually, we realized that as we are moving to CTs, because you have volume scans, for MRs, because you have multi-sequence and volumes over there, you need to develop more compression engines even for all of them. And that's when we came up with this idea of what we call as a custom encoder, which is for a modality you have a different kind of an encoder. So your encoders are always modality specific, but then you have your decoder, which is a single decoder. So your decoder doesn't know what modality is over there, it can just decode whatever comes to it. So that was the fun part of how we developed, and this is the story about going through that journey. Because that itself took us about 3.5 years, and we took about 3 months to write down the manuscript when we had to write down the complete story. That was that big. So the primary idea is from this fundamental theory, which is called as information bottleneck principle. So what it essentially means is that you can any kind of a trained neural network can be more of also thought as a Markovian process, and this is a very well-known proven thing over there. So if that's so, then what happens is that you can come down to a certain point, which we call as a bottleneck point, where you have the least, but that least amount of, say, representations which are needed to store the complete data. So if I tell you in very simple terms, how many of you know about PCA, or Principal Component Analysis? You guys know about it. So PCA's fundamental thing is that you would like to boil down any data of any dimension to its inherent intrinsic dimension. You go anywhere lower than the intrinsic dimension, then you are just going to lose out on the information quality over there. So what you essentially see is that your mean square error keeps on increasing beyond a point of that intrinsic dimension over there. So you have a similar kind of a thing available within any kind of data or image data. The only thing which you put down over here is that in PCA you are assuming that your basis vectors are all orthonormal to each other. Now here, in case of neural networks, it does not necessarily mandate this orthonormality condition, which means that I am somewhat similar to an ICA, where I don't have that orthonormality condition, but then I can still come down to a intrinsic lower dimension and keep on representing. So if I can catch that lower dimension, then I'm not going to lose the relevant information within the data. And that's the fundamental hypothesis based on which we started working on this. So to give you a glimpse about what these modality specific compressors or encoders look like, it's something like this. So if you look into this table, on the left hand side, the left hand first column, you have different data sets. And then they come from different modalities. So CBIS DDSM is a mammography, it's an extra mammography single film data sets which have of sizes almost of 4K. In breast is also mammography which are sizes less than, so they are, you can more of compare them to a standard HD size image, so 1080p is what they would be. Chexpert is chest x-rays which are lesser than 1 megapixel in size. Mura is for bone x-rays. Chaos CT is for CT of abdomen. Chaos MR is MR of abdomen, and their sizes, their slice sizes are lesser, but the number of slices is more. So that way it increases in the total amount of data. Luna is for lungs. MRNet is knee MRs, and IELTS 18 and IELTS DWI, PWI, they are for neural scans. So they are MRI scans of the brain. Now for each of them, you have the architecture of this model defined by a term called as depth. Depth is essentially the number of layers. So it's not essentially the number of layers, but a factor which guides the number of layers which I take. And width is the number of convolution kernels or the number of filters which you have per convolution layer. So that keeps on changing. So if you look into here, you can pretty much see what is the amount of diversity which we had when we changed from one modality to another modality. And that was the customization which had to be done. So based on this, we actually have a much detailed version of this one going down. I mean, only this story about building compressors for 3 years at ICME next month. But before that, let's get into what is the basis for compression. Now, the fundamental theory is still within what we call as Fourier series. How many of you remember Fourier series? Fourier series. Everybody remembers Fourier series. Okay. So Fourier series was the first hit at trying to solve a compression problem. What it said is, you have data in your time domain. You're just going to break it down into an alternative presentation where you say something as a basis function, or over there it's basically going to be your fundamental frequency and harmonics, and you will have a weight associated with each of those waveforms over there. Now if you take a weighted summation, then you are able to again get back your signal over there. The more the number of components, the better and better it becomes. But then there is an inverse relationship. It is, you have lesser number of components, which means that you are consuming less amount of space to store that data. But the lesser the number of components, the more is the error in reconstruction. So as in over here, if you have a square wave, you would get most of those errors with missing number of components at the points of inflection. So wherever there is a change in the magnitude which is happening. Instead of that, so if my fundamental waveform was not a square wave, which is the toughest to store with a Fourier series, if it was a sinusoid, then I would have gotten down my highest compression, because my fundamental frequency will be the only thing which I obtain from there, and I will have the only non-zero weight component over there I need to store is the one corresponding to my fundamental frequency. Everything else is going to become zero. Now, if I look at that, and let's look at the other side of the logic. What we used in order to do a Fourier series was that all the basis functions were sinusoids. Replace the sinusoids and make them square waves. Then you would see that if your signal is a square wave, you would get a non-zero component only for the fundamental frequency which matches the fundamental frequency of your square wave, For all other harmonics, you would be having a weight of 0. So you have only one non-zero component which you are going to store. So coming from this point, I'm trying to get into a prelude to this problem is, if you are able to learn a basis function which is apt for your data, then you will have the minimum number of bits which you will need to store in order to compress your data. And that's what we were doing in the earlier days when we had this different kind of compressors, because every data has a different compression basis. But then my decompressor for a Fourier series, if I now write my Fourier series in this way, I will tell you what kind of a waveform, I will tell you the frequency of the waveform and the weights of the waveforms, synthesized. So if I give you these three information, you don't need to know whether your decoder can now be a generic decoder. Because you are just going to tell it what? Function, sine, triangular, square, fundamental frequency, duty cycle, weights. Done. This is what I am solving. So I injected one additional component over here, saying that I will also make a compressor which is intelligent enough to tell me which waveform should be my basis function over here. That can solve. So now based on that, we go back into how standard compression classically has been solved. So I'm looking into, so compression will have anyways two different factors over there. One is what we call as a energy compacting transform, which basically compresses the energy into lesser number of basis functions over here. The other part is what we call as a code length compactor, and that's another lossless compression mechanism over there. So you need lesser number of bits in order to store it. As an example, say that you have an 8-bit number, but there are only 4 possible such numbers which exist. So you know that if there are 4 unique numbers, there are just 4 unique states. So at max, I would be needing only 2 bits in order to represent that. I don't need all the 8 bits. So that's my code length compactor, which comes over there. A classical thing, which a lot of you have studied, is called as half-band coding. Right? So any compression basically relies on this. One is you want to compact the energy, which is come down to these basis functions. Now, every basis function is not equally probable. There are few which are very probable, there are few which are less probable. Whichever is more probable, you give lesser number of bits to store it. That's what we'll go with Huffman theorem. And then you can have a compressed file, which is of the smallest size. Now you change around with your basis functions, you change around with your coding strategies, and then you can have different forms in which these can be brought down. So if your basis function is just a DCT, you have a JPEG image compression technique. If your basis function is a DWT, you have J2K image compression technique. If you have some higher order of wavelets, then you have HEIC or HEIF. Have you seen that format? I mean, currently I think most of the phones are supporting HEIF, high efficiency image compression formats. So you will get all of these different forms over there. So from there, we started getting into this whole game about how do you compress medical images. So this is from the first endeavor which we had at CBPR, and the idea was we created this kind of a modular structure. So this looks like a autoencoder structure. Does it or doesn't it? Does the architecture look like an autoencoder? Because it is an autoencoder. It's just a simple convolutional autoencoder. So the way in which whatever kind of transformations you have in the encoder, you have an inverse of the same kind of transformations in the decoder. Except for the fact, you don't have any message passing between the encoder and the decoder in the matched depth. So say a unit kind of an architecture will not serve this purpose. But if you're looking into something like a segment, that will work out because I just need that one clear and clean latent code which comes over. And then these blocks were not just simple convolution blocks, but they were two different, like there was two successive convolutions, one with a stride of 1, another with a stride of 2, so that you have a downsampling operation also taking place over there. And then you wanted to invert the same thing, so in an up convolution block what you had is a convolution with a stride of 1, and then you had a subpixel shuffling, so which essentially increases the spatial span but decreases the number of channels over there. So based on this is what we could train. Now, out of this pair of images, one of them is an actual mammogram, which is uncompressed. The other one was compressed and then decompressed and is shown over here with this method. And then this has roughly about 300x of a compression ratio. This is way beyond. I mean, 300 times is way beyond what you can achieve with JPEG and JPEGs. With the current recommended standard for using JPEGs and JPEGs for mammography compression is limited to only 10x. You cannot go anything beyond that. With J2K 10x, with JPEG it's just 5x. We are speaking about 300x. Now, can you identify? How many of you think that left-hand side is the uncompressed or the real one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, how many of you think 50? How many of you think that the right side is the original uncompressed? I think roughly around the same number of people think. And then how many of you are undecided? Yeah, that's the majority, undecided. I mean, that's the best thing for me. For a person who develops these kind of engines, we really love that you're undecided. In fact, I'll tell you the stats. So this was done over 200 images, shown to 25 radiologists who actually practice mammography reporting on a daily basis. They report about 5 to 10 mammograms daily. The result was 52% confused. So it's nearly that you are just confused over there. So that's the stat. Now, when we finish this, which one? I can tell you. I know the clues. So the left hand side is the original. The right hand side is the compressed one. But on this screen, you will not be able to make it up.
Yeah.
So I have the 16-bit. I have a 14-bit screen, not a 16-bit screen, so I can still somehow get it. So there is a bit of smudging which happens over here, but you have to really be an expert to be able to spot it. Yeah. Lossy. It's lossy 300x. With lossless, you can go up to 20, 30x, nothing more than that. This is lossy. You want to go high density, you have to go lossy. That's the challenge. I mean, you want to go lossy compression, but you don't want to lose clinical insights. That is, you lose out a key indicator for a disease, you're gone. I mean, here's the key indicator for a disease. So, these white spots which you see, these are microcalcifications. These are calcified discs, these are microcalcifications. These are indicators for my disease. If I never had these kind of small spots, but I had only these larger calcified discs, this would have been a benign case. Because I have trace microcalcifications over here, that's the reason why I would still be calling this as a malignant. There is a pure sign of malignancy, well defined.
Sometimes basis functions might be there under some frequency might get stop line the pure sign function. Yeah, and that in that case it would be lossless, right? Particular basis function.
So you are saying that my input was a sine wave, my basis function was a sine wave, and then I got it. Yes, then only it would be a lossless because you have only one single component over there. If you want to make it lossy, you will lose out all our components. You will have E3D compression factor in that case. Yeah, that I agree, but I mean, for images where you get that kind of a distinct function as such. Okay. Yeah.
Will this compression system works on normal images as well, or just in the
It works.
What? So why is this not commercial application?
So we are working on it. So essentially, it's not so fast. So I will tell you. So you have HEIF on your phones. Okay. Do you have any idea when HEIF was first published? The company which invented HEIF? No. Not Apple. HEIF was invented by Nokia. In the year 2002, the first standard was published in 2005. You did not have a commercial silicon available with HEIF on your phones until 2022. So it takes 15 years. Okay, for video compression standards. So, which is your favorite OTT service? Netflix. Netflix? So what is the compression of Netflix? No idea?
Yes.
So current compression is HEVC. Okay. Now, what is the current compression on Google Meet or Zoom? Not H232. So HEVC is H235. The current compression on your Google Meet is VVC, H266. So your Netflix is anyways running roughly 13 years behind it. So HEIF was what was for images, you had HEVC for videos. So coming around the same time because they're more or less the spatial compression is on similar kind of architectures over there. So HEVC which you have today, and Netflix got HEVC introduced in 2022. Till before that, they were not even HEVC. It was just AVC. Huh? YouTube is a different compression standard which is called as web video. Google has its own. And actually, YouTube is my competitor in that case. Because that's the one which uses a deep neural network in order to compress videos. YouTube has a far advanced technology. YouTube uses a similar kind of an architecture like deep neural network. For the live videos, yes. No. When you do a YouTube live, so when you do a Hangouts on Air or YouTube live, it just uses HEVC because the issue is that the decoder part of the codec which they have is a softwareized implementation which runs on Chrome or any of these browsers. So you have a JavaScript based implementation with something called as a timing variable which acts as synchronous and then it works out. But you don't have a on-device encoding system. So your compressor for most of your phones or your laptops or everything is still based on a single SoC which is on HEVC. So you have a SoC solution for HEVC. That's why whenever you are uploading a video on a live thing, it's always HEVC. So you still don't have hardwareized codecs for VVC as well. So you need to wait for it. Or maybe if Google starts selling hardware, those SoCs on Chromebooks, then maybe Chromebooks will have that. But seems very unlikely. Looking at how the tech industry works, I know that it's very unlikely. Yeah.
Since we talked about it earlier, how do you preserve the pictures needed to classify this image? Because this will depend upon.
You minimize distortion losses. That's it.
So how do you actually ensure it?
So the only way of ensuring this one, I don't have a rigid enforcement mechanism as of now. We are working on that generation because we wanted. So 700x which I show over here or 300x, I'm still not happy with this. So I want to go even beyond. Right? When we try to do it for OTT service providers and movies, or even for autonomous driving, we want to go all the way up to 1000x. Like really very high density compressions over there. And there we need certain enforcers, but I'm not going to discuss that right now. Because, that's something I'm working on, so I'm not supposed to tell you guys that. But I can give you hints, it depends on how much you can pick it up over there. So, this is about the story of what we did when we wanted to really expand it. We got a good success only on mammograms, but then if you take this model directly and use it for other images, you're not going to get down the same kind of a performance. In some cases it was good, but in a lot of cases we were seeing bad performance. And the other point which we noticed is that the latent code space, which is file which was getting generated, was hugely sparse. And what that indicates is that these basis functions are going to be tuned. You need lower number of basis functions, you don't need them. And that's what I was showing you. So on that table you had different number of width, you had a different depth, and all of this is together what is deciding what is the order of complexity of the basis functions and how many basis functions you have. That needs to change from application area to application area. So when we decided to go with that thing, we divided this into a modular structure. So what we had is, now I will show you this. So this, you guys get a once in a lifetime private review into deep dive of what makes up the IP of my compressor. And I'm giving to you for free. So if you have the courage, you can take snaps as much as possible. I don't have IP restrictions and I throw it out as an open challenge. If you can train one, build it. Because designing this architecture is the easiest of all the things which you'll have to do to build a code. So build one. I mean, I really want you guys to go and build one. It wasn't a joke. I mean, I'm throwing open the exact architecture over here. We published it as a journal paper so that people start doing it. And that's the reason next month I'm actually doing a tutorial at ICME. It's the International Conference on Multimedia. So I'm doing with the multimedia guys so that I want more people to see that they start getting using and doing it. Because the IP is not there in the architecture in any way. And if you want to lay down, so Google has its own deep learning based compression engine. Apple also has its own deep learning based compression engine, but Apple did not make it by themselves. They just went and shopped around for a startup. There was a California based startup called as Wave 1. They just bought up Wave 1 and then did it. So this is what everybody else is doing as well. So even you guys can do it. And you don't know when, so Wave 1 got acquired for not disclosed amount, but what most market pundits are guessing is, I mean, you have people who look into your valuation and then they can say what was the possible acquisition for $35 million. 7-people company, just an image compressor is what we're building using a deep neural network. Okay, so this is the first level preview. So the network is built up using this kind of a module over here. So in the blue, you would see 3 distinct blocks. One is what is called as an input conditioning unit or an ICU. You have a stack of cascaded blocks which are called as digest units or DU, which makes up the digest component over there. And that's essentially where all of your basis functions get learned. And then you have an output conditioning unit, which essentially maps it onto a fixed length tensor. The tensor which needs to get generated over there needs to have a fixed number of channels, and that's the job of this ICU. So you would look into it that ICU, independent of how many Ds you have, it can always take in fixed 3-channel RGB representations. The OCU over here will always produce a 16-channel representation, which was over here, independent of what is your input number of channels or how many channels you have in the digest over there. Now, we need to break it further. So this ICU, in terms of your operations, is something which looks like this. So I have a sort of a mnemonic notation for the layer. So conf2d is a 2D convolution layer which has 64 channels. There were 64 filters over there, each of size 3 by 3. It operates with a stride of 1 and with a pad of 1. That succeeds ReLU, and then you have another conv2. But the second convolution has a stride of 2, which means that it would have squeezed it to 1/4 of the size of the tensor, the spatial size. And then you have all of those sensors with the exact sizes being shown as well over there. So this is what goes for an ICU. You may pretty much keep your cameras back because this is a published paper. You can just download it. So if you want, you should be taking a snap of this one so that you get access to the paper. And then go through it. I mean, it's a richly written 40-page manuscript, almost written like a tutorial on what you can do. And every diagram, whatever I show, is present in that paper. Okay. So just click this one. Now that you have clicked this one, now you can keep your phones down and rather listen to the story for the next week. So now this is for your input conditioning unit. You now move to your digest units. Now these digest units are pretty funny. So you have this factor called as D over here, small d. So this d can be a number between 1, 2, 3, 4, whatever you want to choose over there. And that's going to control my depth of how many such I have. And in essence, what it would do is that it would control the depth of this output tensor which gets generated over here. So let me come to that. So you would see that the output tensor which you get generated over here is something like this: m pi to the power of d plus 1 cross n pi to the power of d plus 1. So I choose d equal to 1, that is going to be m by 4 cross n by 4, d equal to 2, n by 8 cross n by 8. So what I can do is I can change my value of d and I can increase my compression factors. This was one of the variabilities which we brought in over here. So what compression factor you want to choose, just set a value of d and you can get a model which is trained for that. Now I need to build up the other other side of the story, which is my decompressor. Now the decompressor also has a similar modular structure. So that will also have an input conditioning unit, you have a digest unit, and you have an output conditioning unit. So this input conditioning unit, what it does is, it needs to take 16 channels and produce a number of channels, which is what I'm processing throughout. So that's 64 channels. The digest units will have similar number of digest blocks, because if I use 3 digest blocks in the compressor, in the decompressor also I need to have 3 digest blocks. Otherwise I cannot really undo the whole effect. And then I have my output conditioning unit, which will just map it to 3-channel output over there. And finally, you would see that if your input is M cross N, your output is also going to be N cross N. And this is a single channel because you just have grayscale images of radiology being taken over here, not color images. So when we do it for multimedia content, that becomes 3 as well. That becomes 3. The next thing is we don't compress on RGB space. We typically do a color space conversion because your multimedia content is typically present in a YUV format. So we have input as YUV instead of RGB, and that has been shown to have much better compression factors than what you would be getting done with RGB. So once you get this, then what I want to do is go forward and understand what would make each of these models and what would be the constituents of those D blocks, or how did I really choose? I mean, I said I have 64 convolution kernels. Why 64? I have 2 successive convolution blocks in one single digest. Why 2 successive? I mean, I could have done something else. So that brings me to what we call as architectural polymorphs of deep neural networks. So if you look into it, so can anybody tell me what is the name of this network which we are showing over here? How many of you do deep learning? How many of you do deep learning? How many of you are trained deep learning models? Yes, few people are raising hand. So what is this network called as? Come on, this is where everything started. This is LeanEd 5. This is LeanEd 5. The standard basic first model where you had handwritten digits as your input and you were classifying outputs over there. This is the standard LeanEd 5 which I am showing over here. So let's look into that second convolution layer of LeanEd 5 and try to create its polymorphs. What I do is, I create another model where I reduce the size of the convolution kernels. Instead of 5 cross 5, I have 3 by 3 kernels, and I increase the number of convolution kernels over there. So instead of 16, I make that 27. So if you do your math over here, you would find that both of these architectures have roughly the same number of trainable parameters. So your 16 into 5, that would be what? 16 into 5 into 5 into 6. Your input is a 6 channel plus another 16 is your number of biases. Now, whatever that number is, the same is over. So you would have roughly around over here. But then, what we see when we do all of this is that you got a model which had a lower compute complexity, which means that we were counting the number of flops which it's going to consume in the forward pass operation. So it had roughly 12% lower compute complexity, and learning capacity is essentially the number of bits. So although I thought like possibly they had the same number of bits, but that's not the case. So what we saw is that we got a new layer which was producing more number of channels, but then the total number of weights it took in order to produce more number of channels was actually lesser, and that was lesser by 39%. Now, one question I have for you: does it necessarily mean that if you reduce the number of weights, that you would also be able to reduce your compute? Would it mean that if your number of weights are reduced, then your compute also reduces? Another example. So my weights got reduced by 13%, but my compute went up by 35%. The only change which I did is I reduced my number of convolution kernels, and I increased the size of the convolution kernel. I made it 7 by 7. And then I can also have this. number of weights increases just by 18%, whereas my total compute increases by 33%. Now if you look between these, in this particular case, the decrease in learning capacity was higher than the decrease in compute. In this case, the increase in learning capacity was lesser. I mean, if you're just comparing, the magnitude was significantly higher than the change in compute. That does not always mean that you have a higher rate of change for your learning capacities. They don't basically relate one to the other. There can be several such architectures which you can draw over here, and they will have their own ways in which they will operate. That's a real fun part. So when you go over there as a network designer for a low resource setting, this is something you really need to keep in your mind. It's never about how deep, how wide. It has a lot of things to do beyond that as well. So the next thing was, we wanted to build these networks, and each modality was to have a compressor of its own. What we started is that instead of, so now essentially you're left in a sea of infinite possibilities. And from polymorphs, you did see that there is a sea of infinite possibilities. I can pick any one of them. Now, how do I have some guided mechanism of doing it? So that's what we started doing. So what we looked into it is that if I break this into some sort of a modular representation, then that should make it easier. In a way that the cost of compute or the number of flops which it is going to take keeps on scaling with the depth and the width, and also something called as its compound scaling factor. So what it essentially means is that if there is a factor called as alpha, and I am increasing my number of depth by a factor of alpha, so which means that initially I had a depth of 1, I make alpha equal to 2, so which means now I have a depth of 2. That would indicate that my compute will also become down. Roughly, it becomes down. If I look into width scaling, which is the number of convolution channels I have, the number of filter elements in a convolution layer, if I scale that by a factor of beta, so say initially I had 16, I make it 32, which means that I am increasing by a factor of beta over there, then my total compute will increase by a factor of beta square. So my compute doesn't double, but it becomes 4 times more. And then you can use another factor called as phi, and then get this kind of a generalized equation whereby we say that if you have alpha beta squared to the power of phi, then your net compute scales up by a factor of kappa to the power of phi. So I can choose my value of kappa, which is my factor by which I want to tune, and I can have alpha beta and phi taken up. So this becomes a constant optimization problem, essentially what I'm solving over here. Now with this constant optimization, what you would come down is to this point that if I have a base architecture which looks like this, I have only one single depth and I can find what compute it looks, then if I increase that one by scaling, then I can have an empirical estimate of what will be the scale up on compute which will happen over there. Using this concept, we started coming up with how to build these kind of custom compressors with a generic or one single decompressor. So now this becomes an architecture search problem. So whatever you see on your right hand side top corner, on your left hand side top corner as one single square of a different color is essentially a different architecture which we are training. But then we don't train it till end of life, we train it for just a few cycles, which is say some 5 epochs or something. And we just see whether my loss functions are decreasing or not. Now I have different architecture. That does not necessarily mean that everybody is going to train at the same rate. We just pick up the ones which train the fastest, which will have the minimum mean square error over there with these 5 epochs of training, then form a set of candidate features over there. Now these candidates are going to come down on a modality specific. So what happens is I have these possible set of architectures which are spawned out by changing alpha, beta and phi. I have some 11 data sets on which I want to train. I train each model just for 5 epochs on each of these data sets. Now for any given data set, I can pick up the top 3 models which come down over here. Now using those models, I can now go down further. So what I do in the next step is that now that I have these compressors which are specific to each modality, I need to make a decompressor which is generic to all the other modalities. So pick up these compressors, pick up all the decompressors, create an average architecture out of all the decompressors over there, then train it jointly with all the modalities. Which means that when I'm training with mammogram, I have the compressor trained only with mammogram, decompressor trained with mammogram, treating it with chaosity, compressor only with chaosity, decompressor with mammogram chaosity, and all the others. So there's an iterative minimization process in which it keeps on going, and finally we end up coming through to your final end product. But over here, still D is a very important guiding factor because you can keep on changing your D, and you can have different Ds for different kind of compressors and decompressors for different modalities. So finally, when you come to this stage, what happens over here is that for a depth of D equal to 1, I will have one set of compressors and a single decompressor. For depth of 2, I will have another compressor decompressor. For depth of 3, I have a compressor decompressor. Depth of 4, I have a set of compressors and decompressors. And then the next thing is, how do you choose which is the best? So you will have to come down to your rate distortion curves and then find out like which is my convex hull over there and say that okay, this is the optimum thing which I want to choose for which particular kind of a modality. Now after having done that, if you look into the performances, so this is something from an MR of a knee. The left hand side is the original image. The middle is the result of decompression for our method. The right hand side is a JPEG at similar performance ratio. And I think this was, I'll have to check the next table. So this mentions the compression factor. So that was MR of the knee, which is MR net. So for D equal to 3, it had a compression factor of 39.40. That's what you achieved over here. So as you keep on changing for every D, you had this net compression factors which were coming out from. Now from there, we again got back to our mammogram. But this is compressed, decompressed using the new compressor. And then we also had the same kind of a 300x compression factor on this one. Now I ask you the same question. Which is original? Left or right? How many of you support that left is original? Okay. How many of you support right is original? How many of you are still confused? So how many of you are confused because you are sleepy and I am speaking to boring things? I mean, people are confused, but then you cannot say that. I mean, that would be impolite to say that to me. Especially when I'm standing on the stage. Okay, so over here, right is the original. Over here, right is the original. So if you want to even get your hands on this, then this is the whole source code, the whole IP in front of you. You can snap the QR code as well. So I'm making one of the world's most competitive IPs available over here. A $20 billion industry in front of you. Build whatever compressions you want to build. And by the way, this is actually a part of OpenVINO toolkit release. So this is certified for direct product inclusion. You want to use these networks directly and build your own compression engine products. You don't even have to train. So whatever models we have given you after training, that's already a certified model. So these are all certified models which I'm doing. These are so like one of my clients is GE for these models. GE in the recent software release, I mean the one which got released in April of 23, in that particular patch they already have this one included. There's something which is called an experimental high density compression, and then they have this one. I had a call with them yesterday. Got the good news. So now this was one part. A lot of data. Then what do you end up doing with data? Now coming the next part of it is yes. There won't be any information gain ever with compression. If there is an information gain as a result of compression, you have introduced noise into the process. So, okay, the term you are possibly referring to is called as visual appearance or clarity, something of that sort. Information is a very numerically derived term which comes from information theory. So that has nothing to do with whether it has a high contrast or low contrast. Now all of this issue is because you have these lights over here and you have a projector which is a 8-bit projector projecting with a very low resolution, honestly speaking. So you need to look it on a full it's green and you will be able to see it. So there is never an information gain. In some cases, we did see that there were ringing artifacts and hallucinations which led to a perceptual increase in contrast, which was not what should have happened. So we did work out around those as well. Okay, so now coming to the next part of it, which is are we doing the time? Yeah, you're doing good with the time. So this is about, can you make microscopes fast? Simple, bottom line. So this company called as Couple, they walked up to us. It's a digital company in Bangalore in India, and they have the world's first AI certified microscope, and which actually is used in a clinic. So in the last slide I will show you one of their own clinics. So in fact, the fun part is that whatever reports you get from this, you can actually use it for insurance claims. It's certified to that level, and it's an FDA certified product. So what we had to do was very simple. They walked in with a simple point. It's like my AI models work on 40x objective magnification. When I acquire an image with 40x objective magnification, it takes me roughly 30 minutes to acquire an image. Can you make that faster? Because my AI model takes less than a minute in order to analyze that image. Simple problem statement. So what we had for us is how low can you go, and if we can go lesser than a minute, we would be really happy. So we had that target, we have achieved it, but that did not go into the certification part. I mean, that's not part of the product release. The product release was capped at a much conservative zone of compression. So the idea was something like this. You had real images from 40x, very high resolution images coming down over there, but then you wanted to simulate or super resolve and get down the appearance similar to that when you had access to only LR or low resolution images which were acquired at 10x. So roughly you have to do a 1:4 blow up in the resolution of these images, what we are looking at. So the idea was that get this kind of a model trained along with Turing test. Now these Turing tests are essentially similar kind of discriminators. The only difference is that in a Turing test discriminator, you always show a pair of images. You don't show one image at a time. That's the only difference which happens over here. And then you ask it like to find out like which one is real and which one is fake in that in the order in which it comes from. What we found out is that because your WBCs were much lesser in number in any field, so and they are the ones which have the highest amount of texture, and that's the key element for your diagnosis as well. So just using this kind of a broad image level Turing test, it does not always work. So we also needed to go down with region-based Turing test. So get down region proposals where WBCs are, and then do a Turing test on the appearance of WBC itself. So that was another additional level of Turing test which we had to add over here. So once we trained it with that, we ended up getting a model which is like this. The end result is something you can see. On the top row, what you see is those WBCs really blown up. You might even see pixelations over here, which is pretty fine because it's blown up to that level to match down like 10 pixels on your screen will be matching to a single pixel on the image. It's blown up that much. So on the left hand is the real one. On the extreme right is the one which we get from Turing test. And then you have this complete spectrum. So if you do a bicubic interpolation versus you have a standard SRNet from Facebook AI. And then the last two were the ones which we had done. So you can see that you're starting to get down these crisp granular patterns over there, which are associated with granulation within the chromatin material of the nucleus. And that's a diagnostically relevant feature, by the way. So similarly, we tried doing it on tumor images, which is the one on the left hand side, on the lower row. And that lower row, so upper row is something which is proprietary images from the same company. So the lower one is what we had given down in the paper so that you can have reproducibility of results from a public data set. And this was on histopath. So you had a different model to be trained on histopath. But now you are able to get down your textures. You are able to recover those textures, which you were never able to do. I mean, you can see how much it's faded off, as if like there is water smearing on top of a painting. So this is the power of what we were able to do. Now let's get into where it stands. So this is the machine inside which it sits. It's a digital size scanner. There's a company which makes it. There's a company which does your tests and gives you report. So it's a diagnostic path lab without a pathologist. You don't have a human pathologist. computer generated, and below the report you have a line which says that this is generated by, this is a computer generated report, date, time, so and so, machine serial number and machine DNA so and so is what it did. That's it. The whole AI sits inside the machine, nothing on a cloud service or anything. And whatever AI, including the super resolution, whatever runs, it runs on a very simple Intel Core i5 4th generation CPU without a GPU. I mean, that's the current version of the model. In fact, an earlier microscope had a Raspberry Pi on which most of the AI used to run. It used to be so frugal. So if you're thinking like it takes a lot of efforts, nothing. Now, coming to the point of what did we do with super resolution? The break-even point was something like this. When you are acquiring at 40x, which means that you are acquiring at a very high resolution, which means that the total field of view of a whole slide which you are covering is much smaller. You'll have to take a lot of snaps and then stitch them in order to get the complete slide. When I acquire at 10x, my field of view is more, so I have to take lesser number of snaps, which means that I am obviously faster. The number of snaps I have to stitch is lesser, so I am again faster. So if I do a thumbs rule, so between a 10x and a 40x, you have a 4 times of a speed up, which you will get done. Because with 40x, how many number of images you will have to take? With 10x, you will have 1/4 of the number of images which you will have to take. The only thing is that you need to super resolve and get down that resolvability, which we are anyways doing it with a software unit over here. That means that what used to consume 30 minutes is now just a matter of 8 minutes. That will lead to lesser amount of wear and tear in the microscope, which means that the mechanical component life has increased by 4 times as well. Now, over here, what you have in this table is an example of scale-up factors, and these numbers which you see is the performance of that AI model when compared with what it was doing with the actual 40x image. So we found out whatever was the diagnosis from the actual 40x, we gave down corresponding super resolved images, and then we saw what the performance is. So with when you have a 10x, when you have a 4x scale-up, which is like from a 10x image, I'm resolving to 40x, and then I see it. So you get roughly around 99% of a match. So yeah, roughly around this. So when I have a 9 times scale up, a 9x scale up means that I have a 40 divided by 9. 40 divided by 9 is something like 4.2x of an objective magnification, or a 4x of an objective magnification. I scale it up all the way up to 40x, and then I do a final diagnosis. I have roughly around that. I just have 1% lesser, 98%. But you can imagine this, right? I just need a 4x thing. Now when I do a 16x, 16x would mean that my objective magnification is just 2.5x. Now what's a 2.5x magnification? How you use those magnifying glasses? So if you just look at a glass slide with a magnification glass, you get roughly between 2x to 3x of a magnification. So now what I'm saying is I can do a digital pathology without a microscope. Just put a magnifying glass in front of my camera, phone camera, acquire that image, run it through this super resolution, you get your super resolved version, which is equal to 40x, and you can have an accuracy which is about 98%. This is what is going to change how healthcare delivery will be done to the last mile. I mean, a lot of places it has already started doing it, and these are models which are going to go all over there. Now from that, I'll change the story, and I think by now most of you guys are super saturated. Neurons will not work. I had a pretty packed morning, and then I'm keeping on blabbering with a lot of product scale AI going out. The idea was, can you use generative models in order to learn imaging physics? So imaging physics for us was imaging of ultrasound machines. So can I have generative models which can generate ultrasound images by looking at digital phantoms? So I draw down certain anatomy and I tell what is the speed of sound in different tissue levels, and can I now generate ultrasound images from that? That's what we wanted to do. So let me skip this part of the general physics of thing coming back. Too much of thing. Yeah, this would be an interesting part. So till around the like early 2000s and late 90s, Field 2 was one of the predominant software programs which was available to do this simulation of images. The thing is that it would take you roughly 3.5 hours to simulate this kind of a say 80 by 100 pixel ultrasound image. Now, if you would have essentially done the image of a fetus, then you would be getting down 30 frames per second coming down. So it does not anyways make any sense to simulate because your simulator is too slow. So that's what we wanted to crack. So there was a paper by Bamber and Dickinson from about 1980s. So I was following that paper and then when did I write that code? I forgot. So somewhere around 2010 or 11, I had written this first bunch of code which was on MATLAB. You could use simple convolution operators and do a pseudo ultrasound simulation over there. But it was fast. I mean, you can get down images something like at 100 frames per second simulated. It was that fast, and purely on a CPU, not even a GPU. So what it had was pretty simple. There was a noise model and there was a propagation model which was tuned to the frequency of ultrasound so that you are able to simulate and get spectral maps which look like this. Great. Pretty happy to do this kind of small patches, but when we wanted to do it for a full scale image of the artery, a cross section of an artery, this is what we got. Whereas the real image is what looks like this. The simulator is way off than what the appearance model of the real one is. And that's what we wanted to bridge. So we got back to the board and thought that possibly these convolution kernels which we have over here are not rich enough to define the physics. We need to play something around with it. And that's where we got this idea. Why cannot you use neural networks in order to learn convolution kernels? Which means that now I'm learning the physics of that signal model with the neural network. So you are solving different things. I'm asking you now that your neural networks are learning physics phenomena as well. So that's the interesting part. Just this is a simple animation on convolution. Each of you know it. It's just part of the standard slide deck, so it is there. So now when we built this network, what we did was something like this. You take that sort of what we call as a level 0 simulation coming out from the rigid model, and then you have multiple convolution kernels with which you can induce a lot of degradations. You have multiple channels which would come down, but your ultrasound image is not a multi-channel image. You need to fuse all of them into a single channel. Have a nonlinearity on the range space. Get down a single convolution kernel so that you end up merging all of those multiple channels of degradation and get down a single convolution output, a single channel output, which means a single grayscale output over here. The challenge, however, is that if you want to train this directly with mean square error, you would need pair of image patches over here. And getting that many large number of paired images which are annotated for their speed of sound is really going to be tough. So that's where we came across these generative models and started experimenting with adversarial learning. So the idea we had was something like this: that you can give an image, you can get down some degraded version of an image, you can think of getting down a distribution over there from where you can do it, but then you'll have to define these for your ultrasound. What is the primary problem over here? So now we started looking into this basic concept of what we call as an adversarial transformer. So what it does is, you have a digital phantom, you have a generative model which generates some images. You do a mean square error minimization in order to have geometry distortions at least corrected for. So whatever geometries wherever they are supposed to, they are preserved. Then what you do is you have a discriminated network over here, and this discriminated network learns in comparison with real images, and then you update the weights of the discriminator as well as the generator. A standard adversarial learning paradigm, nothing different over here. So what we did is, we had these images coming down from the digital phantom. One change is, instead of doing it in the Cartesian coordinate domain, we took images in the polar domain. The primary reason being that ultrasound, when it propagates radially outward. So it's sort of space invariant in terms of the point spread function in the polar domain, not in the Cartesian coordinate domain. That was a very important thing. Convolution is space invariant, but then you need space invariance in what? I don't need space invariance in Cartesian coordinate for this problem, I need it in polar domain. Now you got this first stage of simulation results, take it forward and then break the problem into two different transformations, adversarial transformation. One is where you would like to get the amplitude of each of those packets. So you have a lower sample size, the 64 cross 64 equivalent of a 256 cross 256. You train it for your discriminator loss minimization as well as the generative loss minimization, both of them. Now once you have your this part trained, you freeze this part of the network, you take the output from there, and then you train another stage over here which will look into the spread or the point spread function of these impulse functions over here of the speckles. And you use a similar kind of a concept, except for the fact that now it's on a much larger resolution of 256 cross 256, which is that of the origin privilege. You use your discriminators, you have trained it, and now comes the moment of truth. And one more quiz for all of you. How many of you support the one on left? So what is it? I mean, is it real? Left is real. Okay. How many of you support right is real? How many of you are confused? Again, majority is confused. Okay. But here I have a distinct clue, I will tell you. So, the right is real. And why it is so is that because I see this distinct discontinuity over here. And there is a reason for that discontinuity. So, this is like, there is a single probe ultrasound which scans within your artery. And it has a screw-like motion, a helical motion. So between 359 degree and 0 degree, you basically had a shift, a lateral shift, a pitch. That's why you will have a discontinuity. And that was the clue I was using in order to identify which one was real. But other than that, it's really not possible to do it. Now standing on top of this is the next part, which is the images are actually acquired in 3D. I was showing you one slice in 2D, in a squeezed in projection. Can I have these 2D slices and create the image in 3D? So this is a dimensionality Debdoot, what I was indicating. You had one missing dimension, which is I want to simulate my images in 3D, but I always see my data in 2D. I never see my data in 3D. I don't have my data in 3D available to me. So can I now do that? So there was not much of learning involved in this one. What we had done is we first tried to understand the wave propagation physics. The idea is something like this, that when you have an ultrasound, you have a wave pulse which is propagating forward along one direction. Then you have it propagating along two orthogonal directions. Because there is a plane which is orthogonal to it. So you have one line and a plane. So along this axis versus along this axis, even if I twiddle it, it does not actually change. The waveform is still the same. So that's the idea, that your lateral beam profiles along the x or the z, both of those axes are still going to be the same. So what can you do? One thing is, you can represent the complete image formation process like this, over here for a 3D case. Now if that's the scenario, then what I have is, in my 2D case, whatever I am simulating, I am getting certain outputs. Now if I can take this model and map it to a 3D case, which is through a certain substitution operation which we call as zero-shot adaptation. So you don't train a model anymore. You just have one trained model, but you're just fiddling with the geometry of how convolutions operate. You will get down your 3D. Now, how we made this possible is using a concept of multilinear separability within CNNs. So what it does is something like this. So say I have a 2D convolution, which is something like this. So you have an input activation space, you have a 2D kernel, you have a bias, you get your output. A 3D case will also give you a similar thing. You will have a 3D activation space, a 3D kernel, you will have a bias and an output. Now I can break it down. So a 2D convolution kernel can be approximated with a convolution of two 1D convolution kernels. Yes or no? Shifted 1D convolution kernels. So you can have now these represented in two different directions. So over here, this is a X kernel and this is a Y kernel. Here this is an X kernel and this is a Z kernel. So these Y and Z is what lies on that plane and they are quid level. They have the same kind of a behavior over there. Now if I can train a model like this, then similarly I can go on to my adaptation onto 3D, where what will happen is that this 2D plane can be represented as either of these three possibilities over here, where whatever propagates along the axial has to remain the same. That cannot be played around. But what I can play around with is this plane versus this plane. So if I do that, then I can end up writing my convolution filters of this form, where these blocks will have this kind of a representation. So you have without bias 1D convolutions and a bias which is separately added through a 1x1 convolution over there, which is my merger function. Now that I have this kind of a representation, which incidentally also has lesser number of learnable parameters than trying to do it on a full 2D case, we end up being able to simulate something like this. So on the top row is the real one, which was done with a scan, and then you had different cross sections and slices being seen over here, and then this is an oblique section, so we just do a slice on an oblique way. So in the bottom one, you have the same thing which is coming out from a simulator, and you can see how close they look like right now. So I did not simulate one frame at a time, I just simulated the complete block in one shot by learning just from single frames. Now I'm running out. And 5 minutes, and I think I will finish in 5 minutes. So the next part which comes out is that it's not just all of these low resources, but you also have limitations on compute and limitations on privacy. So one of the ways people go around with limitations in compute is you can get down distributed learning. So one of the things we had in the panel for the morning. So these will be a lot of questions. Like this will be sort of like synergy with a lot of things we discussed in the panel. So you can have multiple laptops, 1,000 laptops, all connected through a network and still solve the problem. But there is a different scale of problem which will arise from that level. So now, what you have within any kind of learning problem is something like this. You have a forward operation where you basically get down your outputs coming from your input. You have an optimization where you are looking at how you would want to update your weights. And then you have a backward operation which is essentially updating the weights with the optimization result. The three fundamental things. Now, in case of a standard way of how you train as of today is what we call as centralized training. You have all the data in one place, residing close to the computer. You feed all the data, you update the model, you get your trained model. The other way of how you can do is you can look into distributed learning, and a standard distributed learning would be something like this, that you have a copy of the same data on multiple such computers. Each of them are training it independently and then synchronizing on a basis over here. But then because you have the same data everywhere, so more or less the models are converging at a faster pace. But then the issue is that the same data has to be copied to every single place. One is there is a network problem. The other is that you cannot have privacy ensured on the data. So today what we are looking at is something like this. I am happy to collaborate with a lot of people in order to train my model, but I don't want to share my data with you in order to train my model. So what I am saying is that data resides private to me. I have captive compute right at the data. Still I want to train a model. Bigger problem. There is no way of ensuring that all the data is identically distributed. And you need to follow an IID scenario for any of your statistical learning. That's the primary thing. You start with like data is IID across train and test set, across batches, across everything, whatever way which you are splitting. Now here you are just violating that because you have no way of ensuring that database. So that's the paradigm within federated learning. So what it does is something of this sort. So you have two parts of a process. One is where what happens with the workers or the clients. So you essentially have an initial model going to them. They train locally with the data over there. Then they send a message back to the server that my training is over. Do you want? I can send you the model back. And then wait for the server to again send them a newer refined model. So what the server does is it gets all the models from all of them, does some sort of an aggregation. So this a simple thing is averaging. A very popular one is what is called as federated averaging. Fed averaging is what even your Google keyboards have it on your phones as well, Fed average. So, but that will work very fine only if your scenario of IID is followed, otherwise it does not work. And that's what we try to solve within a federated learning scenario. So in fact, like the hands-on which you have later on today, that's something which will be, you will actually be doing this federated learning on your own site itself. So I won't get much into that, but let's get into the challenges. So primarily within federated learning, the prime challenges is the distribution of data. One is they are unbalanced. So some clients can have 100 samples, some can have 1,000 samples, some can have 1,000,000 samples. So the amount of time they will take to complete their local training process is going to be widely varied. Then there is non-IID definitely. There is the challenge with the size of compute available with each of the clients. There is challenge with the parameter synchronization. So essentially what happens is you have multiple clients which are going to start sending their models together to the server. So, but the server can access only one. So you have only one single port open to this internet traffic over here. That creates a fundamental bottleneck. And in fact, that is the main problem with this standard distributed learning as well. You cannot solve it because you have the fundamental bottleneck over there. Then you have all of these issues around partial participation of clients and how do you really get limited with that. And then definitely the amount of juice which is left in order to get this compute running, which is the battery. So there are ways of doing it, and I will leave all of that suspense of how to, like this is the suspense which is coming down. Sort of I give you a trailer to what will happen in the tutorial, and then you will be doing it yourself to see it. Next is you're emitting too much of greenhouse gases anyways, and I did promise you that there are models, and instead of telling you just there are models on GitHub, you can just do it. I will actually show you something which we had done, where we actually had an energy meter connected onto the motherboard to see how much is the energy consumption going on during this process. So this was from Mikai 22 Fair Workshops. So the idea was something like this, that you have versatile set of problems. I mean, there are classification problems, there are segmentation problems, there are object detection problems, and within medical image analysis, it's a wide, diverse set of problems which you have. You have diverse set of models with a lot of complexities going on, and then you also have GPUs, but then also a diverse set of GPUs across different generations and how much of power they would consume. So, looking at these challenges, what we wanted to have is, one is address the model complexity, which is, I want to have the minimum number of, so I basically want to go with models which are the minimal in terms of flops and parameters. I also want to have minimum drop in performance if I'm reducing the number of parameters. I don't want a lot of drop in performance. So, and the other thing is that if I'm training between a CPU and a GPU, then what is the speed at which things can be training? So, can I train on the CPU as well faster by changing some, tweaking some certain things on the parameters or the model architecture? So, we were playing around completely on the model architecture space. So, one is, instead of having standard convolutions, you replace them with attention modules. So you don't have convolutions anymore, standard attentions, which are much faster, simple matrix operations without even rewiring the matrices, and you get into quantizations. So instead of having floating point 32, we were starting to working on int 8 representation. And this is not where you train on float 32 and then you are inferencing on int 8, but we are directly training on int 8 itself. Okay, I will just, it's just 2 slides and then I'm done. So when you do this, so there are these two different experiments of different tasks which we did, and then let me skip through this. This is an interesting part. So if you look at the classification task, and we had this multiple set of models. So you had ResNet 18, you had quantized ResNet 18, ResNet 50, quantized ResNet 50. Then we had this attention model and then the quantized attention model as well. Similarly, you had something on your segmentation task as well. So if you look at the performance metric, more or less they are at the same performance level. Now, given that they are at the same performance level, we look into energy consumptions. And this is that moment of revelation. So now you can see that while, wait, where that was? This is the interesting point. So if you compare just energy levels, so in terms of joules, compared to say ResNet 50 or ResNet 18, which is about 50 to 40 joules for the, this was the classification task. When you have a quantized attention model, it takes only 0.35 joules. That's a 100 times reduction in the energy consumption. So instead of 100 kilograms of coal, it's just 1 kilogram of coal. If you look into the classification task, you see a similar order. I think you see a bigger order. I mean, from 979 joules to 31 joules. So 979 joules to 31 joules is 30 times of a reduction. So these are interesting points which we'll start seeing over here as well. So you can just search out for this particular paper. You have a GitHub for this one as well. We have the complete model on Git as of now. So finally, thanks from the group. These are the set of wonderful people who do all the work, and then I just pull up all the slides from their presentation. frustration about it. That's what I have learned as a result of being in academia. If you want to really look at resources, just a small gutter list of journals which people at our group follow, and then I also popularize out that you can look through proceedings of these conferences and journals if you want to look at more details about the field. You can do. And we have this thing of MOOCs as well. So in India we have something called as NPTEL, which does certification and MOOCs over there. So we have these two different MOOCs available, one on medical image analysis, another is on deep learning for visual computing. So if you want to do through a standard, say something like 30 hours of a classroom lecture style thing, then you can also do this MOOC. And we'll again open up for, so there is a certificate examination as well, so you can give an exam, get a certificate, and it's a curated examination, not like you sitting at your home and doing. There are certain centers, and I know that there is a center in Kathmandu as well, because we get a lot of students who do the NPTEL from Kathmandu. So, and most likely, you can check with your colleges. I mean, there are credit transfer equivalents. So, instead of doing certain, if you don't want and you don't like an elective subject which is being offered in your curriculum, you will actually do a credit transfer. So, this is there within that Southeast Asian credit transfer system. It's already a ratified program. So, you get a certificate from IIT, any one of these IITs, in order to get this test done. And so, these are a couple of things which you can as well follow the resources. Okay, so if you still have any more questions, if you are not yet printed, then you can throw those at me.
Any questions? Please raise your hand.
I know people are printed.
I guess no questions.